These are notes on calculating and understanding standard deviation, which we abbreviate to SD, and standard error of the mean, which we abbreviate to SEM, and often just say standard error when we're talking about it. And standard deviation and standard error are ways of analyzing your data so that you can see if the differences in your data are significant. So an example of that is earlier this year when we did the habitat lab, people who did pH found that there was no significant difference in pH across different habitats in the park, which is what you should have found. But some people, based on whatever data they took, found maybe that the pH under the canopy was 7.6 and the pH in the boundary was 7.5, and so said that the boundary was more acidic than the canopy. And the question becomes, is that a valid difference? And that shouldn't be up to somebody's opinion to say, yes, this difference is big enough, or no, this difference isn't big enough. So we've developed these mathematical analysis tools so that we can all agree, yes, that's a significant difference versus no, that's not a significant difference. And later this year, I'll let you calculate this on Excel. But I want you to first start by calculating it by hand so that you actually know what the terms mean and what the calculations are that are being done. It just leads to better understanding that way. So before I get into what the two terms actually mean, here's some sample data. So I took this from 3 different habitats, 1, 2, and 3. I took 5 trials or data from 5 different quadrats, not overlapping. I took the average, which we mean to be the mean, right? I added them up, I divided by 5. And it's the percent of growing plants per quadrat. So one thing I want to say is that when we're looking at standard deviation and standard error, we're talking about the mean, not the median. So often I'll use the median when talking about, say, test scores, because one low score can really bring down an average and make it unrepresentative of the population. You can see that that's the case in habitat area 3 here, where our average is 88, but none of these scores are really about 88. And that's because this 65 is bringing them down. So for something like that, I might use median, but you can ask about that in class if you want more details on when to use mean versus when to use median. Okay, so these are my definitions, which I feel are much better than Wikipedia, which will turn you around in circles as far as what these terms mean. So standard deviation is how spread out the samples of a population are. So if we look back to here at our data, we notice that in habitat area 1 here, the mean is 93, and all of these terms are about 93. Whereas if we look at habitat area 3 here, these samples are incredibly spread out. We go all the way from 97 down to 65. So that's very spread out data. And then habitat area 2 is somewhere in the middle. And so if I were estimating, or if I were hypothesizing, I would say that habitat area 1 will have the smallest standard deviation, and habitat 3 will have the largest standard deviation, and then 2 will be somewhere in the middle. But we're actually going to calculate those to see what they are, and then we'll talk about what those numbers mean. Standard error is how precise your mean is. So it's the plus or minus factor. You can think of that as your mean is still an estimate because it's an estimate of the data you took. And standard error is a way of calculating what could that mean actually be if you happen to take different data. So where a lot of you are familiar with this are on your SBAC scores, those sheets you get. It'll say like your score was, and I'm going to totally make up these numbers, say, why are you not giving me my pen? Hang on. Okay. It might say your score was 2,523. And so that was your score on maybe your math SBAC, I don't know. And that was plus or minus 155. And so that means on any given day, depending on your mood, what you had for breakfast, how much sleep you got the night before, what test questions you happen to get, because you don't always get the same questions on every day that you take the test. Your score really could have been as high as about 2,700 or as low as about 2,400. So that 25, 23 isn't an absolute score. It's sort of a ballpark score. And so standard error lets us know what that plus or minus factor is going to be. And standard error and standard deviation are mathematically related to one another, because the more spread out your data is, standard deviation, the less precise your mean is going to be. And again, we see that here, that we were talking about habitat 3 has the most spread out data, and this mean is the least precise of all of these. It's the least representative of our data. So now we're going to calculate standard deviation, which looks really scary with this big equation here, but I'm going to break it down for you, and really the hardest thing you have to do is a square root. What's interesting is standard deviation is one of the few equations where two of the variables are the same letter, but they're used uppercase and lowercase to tell them apart. So lowercase sigma here is standard deviation. So that's what we're calculating. Uppercase sigma, which is this kind of E-like thing, means the sum of. So you add up a bunch of stuff. And that's true in any equation you'll ever see, uppercase sigma. X is simply a data point. So that's like trial 1, trial 2. X with a line over it is the mean of the data set. And so that's what we calculated as the average. And N is the sample size. And N is always sample size. You hear scientists a lot when they see data say things like, well, what's the N? And what they mean is how many were sampled. So great, you're telling me that the average of these students' test scores was 93. What's the N? Is this a lot of students? Is this a few students? Should I be concerned about this data? Should I not? N is always sample size. All right, so let's take a look at calculating SD, the standard deviation for habitat 1. And we've got a couple steps that we're going to do. So this is simply the data that I pulled over, the top part of that chart. And this here, I've made a new chart, and this is each trial, so the percent of plants. So here's the 93, here's the 96, and so forth. So if we're looking at our equation here, we need X, meaning the data point, minus the mean squared for each data point. And then we're going to add all those up. That's what the sum of means. So 93, here's our average, is 93. 93 minus 93 is 0. 0 squared is 0. 96 minus 93 is 3. 3 squared is 9. 90 minus 93 is negative 3. Doesn't matter that it's negative, because negative 3 squared is also 9, and so forth. So you can see where the 4 and the 0 are coming from. I then add all those up. 9 plus 9 plus 4 plus 0 is 22. So that's this part of the equation here. I've now done that. So this is 22. Now what I need is n minus 1. So we have 5 trials, 1, 2, 3, 4, 5, minus 1 is 4. So I've got 22 divided by 4, and then I take the square root of that. And I'm going to show you that on the next page as well. Okay, so now this table here is just the table from the previous slide. And then I've divided up this sort of second step, which I've already done for you, but just to show you, into this table here. So box 1 here is just the sum of the trials minus the average squared. And so that's this, right? Box 2 then is the n minus 1. So that's this here. And we said we have 5 trials, minus 1 is 4. Box 3 is essentially this minus this. So box 1 divided by box 2, 22 divided by 4 is 5.5. And then, so that's this division operation here. And box 4 then is the square root of what we just took. That's this operation here. The square root of 5.5 is 2.3. So that means the standard deviation for habitat 1 is 2.3. So I've gone through and I've calculated the standard deviation for all of the habitats. You might want to go through and just double check to make sure you're getting the same thing so that you know that you do indeed know how to calculate this, and so that you can ask questions ahead of when you're panicking about calculating it for your own data. I also went through and did what I'm going to call the habitat area 3 parentheses. And I said, I'm going to say 65 here is an outlier since it's so different from the rest. And I'm going to go through and recalculate standard deviation using these 4 trials and taking that out as my outlier. You can sometimes do that. That's where you have to make a bit of a judgment call. Because if I know that an error was made in that, like I know, for example, that I miscalculated the percent of plants growing, or I chose an area that was, I don't know, maybe partially with concrete or something. Let's say I was randomizing my data and some came out on like a path, a concrete path. Okay, I could say that's really an outlier. That's not representative of this habitat. There are other times when I can't pull that out. If I say, nope, that's what I got, it was 65%, there was no error in my taking that, I may need to just leave it in. But I'm pulling it out now to show you how that could change the conclusions I make. And so just as we had predicted though, habitat 1 standard deviation is 2.3, which is the lowest. 3 with that outlier in is 12.6, so that was the highest. And then habitat 2 had a standard deviation of 5.9. And so we can compare these and say habitat area 1's data is less dispersed, less diverse than habitat 2 or 3. But we can also use this 2.3, approximately 65% of the data should fall within 1 standard deviation of the mean. Meaning about 65% of the data should be between, if we're looking at habitat 1, like 95 and 91%. And then 95% of the data should fall within 2 standard deviations of the mean. And so that number has an absolute value other than just being comparative. So now we want to use standard deviation to calculate the standard error. So for habitat 1, this is our equation, and again, it looks scary, but everything is exactly what it was before. So scientists don't change variables around. So n is still this sample size, sigma, lowercase sigma is still standard deviation, and this lowercase sigma with the mean, right, this was the mean, is standard error of the mean. So all we're doing is dividing standard deviation by the square root of n, or of our number of trials. So habitat 1's standard deviation is 2.3 with an n of 5. Therefore, 2.3 divided by the square root of 5, which I wish I had the more updated version of PowerPoint because I could make you a fancy equation, which I can't do. But so I can write it out though. We could say 2.3 divided by the square root of 5, and you can do that on your calculator, equals 1.0. And that is the standard error of the mean for habitat 1. So again, I've gone through and I've calculated all the standard errors of the mean, or standard error. You can go through, I would go through and double check just to make sure you know what you're doing. Remembering that habitat 3, if we pulled out the outlier, now only has an n of 4. So keep that in mind if you're getting both of these, but you're off on this, it's probably because you forgot to change your n. So now we're going to use this to make a graph so that we understand how to analyze our data, right? So far, all we have is a bunch of numbers. So I've made a nice bar graph here where I have population density on the y-axis, habitat on the x-axis. And one of the things you'll notice is that Excel has defaulted to start this graph at 80 instead of 0. It doesn't matter what you choose, whether you choose to accentuate the difference, so that means really show that there's a difference, or minimize the difference. If you started this at 0, these bars would look a lot closer together than they do. And that's really important for you to know, just because it shows how you can use data to get people to think one thing or another. If I wanted to show, like, look, there's a really big difference, I might use this graph. And people looking without thinking about it would see a lot of difference. If I wanted to show, look, there's not a lot of difference, I might choose to start my y-axis at 0. And just be aware of that. There's a whole book called How to Lie with Statistics, where the statistics are real, but you're convincing people of one thing or another. So a really good example of that, going back to standard deviation. Standard deviation, a large standard deviation isn't bad. It just means the samples are more spread out. If I'm looking at test scores of students, for example, there's nothing bad with spread out test scores. It just means that not everybody scored about the same thing. That's not bad or good, it just is. But people can convince you that something might be bad or good based on their bias. So the first thing I'm actually going to do is I'm going to copy down these standard errors so that I can put them on the graph on the next page. Okay, so now what I've done is I've written all of the standard errors below, simply because I can't see them on the different slide. But I'm going to use these to make what are called error bars. And remember what I told you before, that standard error is your plus or minus factor. So that means this mean of 93, based on the data I took and how spread apart it was, on a different day, taking 5 different trials, I could reasonably get something as high as 94, which would be plus 1, or as low as 92, which would be minus 1. So I make a little error bar with these little caps on each end. I don't know what you want to call them, like that. And so I come over here and I say plus or minus 2.6. So I'm going to go 1, 2.6. That's about there. And then I'm going to go down 2.6, 1, 2.6, and so forth. So I'm going to go ahead and do that. Okay, so now I have all of my error bars based on my standard error of the mean. And so now what I'm looking for is overlap. And remember, standard error of the mean is how precise your mean is. So when we're looking at like a really large error bar here, like in Habitat 3, what that's telling me is that this mean is not very precise. And again, we've talked a lot about that outlier, and that's why. But unlike standard deviation, where it simply tells you how spread apart your data is, how precise your mean is an important thing, right? Because if you're then going forward and making judgments based on this data, and your mean isn't very precise, your conclusions aren't going to be very accurate. And so what we're looking for in these error bars is overlap. So we can look and say Habitat 1 was more dense than Habitat 2. And then we're going to look at these error bars and look at the low point of this error bar, meaning on any given day with 5 other trials, I could have had a mean as low as 92. And the upper part of this one, and again, saying on any given day, taken 5 different trials, I could have a mean of, what is that, 87.6. Okay, that's still different. There's no overlap in there. And so that is a significant difference. Habitat 1 was significantly more dense than Habitat 2. Let's now skip Habitat 3 for a second and go to Habitat 3 parentheses. Habitat 3 parentheses has the highest population density. And again, that is significantly different from Habitat 2 if you consider that the low point of that error bar is going to be somewhere here. Okay, there's clearly no overlap there. But that is not significantly more dense than Habitat 1. So because there's overlap, meaning on any given day, we could take with 5 trials, get a mean of something that is lower than Habitat 1, that's not a significant difference. So a conclusion we would have to make here is that while Habitat 1 and Habitat 3 are significantly more dense than Habitat 2, they are not significantly more dense than each other. And this you cover in both your conclusion and possibly your analysis of error. So in my analysis of error, I would talk about why I'm using this modified habitat 3, because I've talked about what error I found in that data point and why I took it out. So I talk about that in analysis of error. Then in my conclusion, I talk about significant differences and whether the data is significantly different. You'll notice here, habitat 3 without that outlier is actually not significantly different from any other habitat because it overlaps with all of them. And that's because the spread was so broad and we had so few trials. So if you go back to calculating both standard error and standard deviation, right, in each case we're dividing by, if we go back to here, we're dividing by the square root of n, or in standard deviation, we're dividing by n minus 1. So in both cases it shows why having more trials is going to get you a lower standard deviation and a lower standard error, which is why more trials is always, always better, because it's going to decrease your uncertainty and make your mean more precise. So if I had gone through here and said, no, I really can't pull out that 65 because I really can't find any legitimate error in it, so I can't say it's an outlier, what I really want to do at this point is say, so what I'm going to do is go take maybe 5 more trials of each one so that I can see if I can get this mean more precise, so I can see if I can make an actual conclusion. All right, this is a lot of math. Feel free to ask questions during class or as you're analyzing your own data. Have a good day.